Hello everyone, you're welcome to my channel. Today I'll be explaining the criteria, the parameters behind the Alkyd resin synthesis, which I've uploaded previously. If you're new to the resin synthesis, you could actually refer to my other video and get to have better insight, because today we'll be focusing on the calculation aspect, the calculative aspect of the Alkyd resin synthesis, and I'm going to be telling you the various things you have to consider, the objective, what you should do to actually be able to synthesize the Alkyd resin, and to know the actual different weights of the reagents that you might be employing or that should be employed in the Alkyd resin synthesis. So first of all, we're going to be determining some factors, but before that, we know what a resin is. A resin is just the binder that's used in the varnish, that's the paint formulation, and I've explained that previously. And the Alkyd, the Alkyd is derived its name from the alcohol and an anhydride. That's where this name came about from. So the synthesis is just what we're going to consider, and there are factors that you need to consider, bearing in mind that we'll be making use of an oil. We have vegetable oil. We can extract our oil via different means, we already know. So we have different types of oil, and there is one specific oil type that we should actually be considerate to using in the Alkyd resin synthesis. So we have a drying oil. We have three classifications. We have a drying oil. We have a semi-drying oil. Then we have a non-drying oil. And for the purpose of the paint manufacturing in your local lab, you should always go for a drying oil, because it helps to allow the surface, the polymer matrix, to be formed and gets dried by either oxidation, polymerization, just the way I've explained it in the previous video. So we are interested in a drying oil. In your choice of oil, it should be a drying oil. How would you know that? That will depend on what we call the saponification value, SV. So saponification value is very important. You need to determine first the saponification value of the oil you are employing for the Alkyd resin synthesis. So the saponification value is very, very important, and the saponification value is just the milligrams of potassium hydroxide that is required to neutralize the fatty acids present in the oil. We know that oils are esters comprised of fatty acid and a triol, which could be a triglyceride, or we could just call the trioglycerol, whatever it is that is present in the drying oil. So saponification value tells you the number in milligrams of potassium hydroxide required to neutralize the fatty acid present in the drying oil. And your saponification value, once determined, should range between the values of 150 to 195 milligram per potassium hydroxide. Okay, now how to carry out this test? I would drop a handout where you can just go through it, just some procedures you have to employ to carrying out this test. For the purpose of this resin synthesis, we'll be focusing on the actual resin synthesis, what you should do and how to do it, how to measure, how to get the values that would be actually that is actually measurable, to carry out the resin synthesis. So that is it. We need to bear in mind the saponification value. So it must be a drying oil. We don't need a semi-drying oil, but it can also serve, but never a drying oil. Okay, and your drying oil saponification value lies in the range of 150 to 195, and that will be perfect for the Alkyd resin synthesis. So this must be determined prior to the resin synthesis. Not all oils are suitable. Okay, the next thing we would be talking about is the oil length. We have what is called oil length, and that's going to serve as our basis for this Alkyd resin synthesis. Our alkyd oil length, we have classification such as short. They are classified into short, medium, and long. So these are just 3 classifications of oil length. The oil length is just but the ratio of the oil that is present in the resin. So the ratio of oil, or the weight in gram of oil you are employing in carrying out the resin synthesis, is just the oil length. So 40% can be considered as short. We have oil length 40%, which is a short. Oil length we have 50%. We can consider as medium. Then we have 60% oil length. Okay, we have this different oil lengths. So these are the oil length. We are also going to be explaining how to actually measure the actual 40%, 50%, and 60% oil length. So the oil length, as I've said, is just the ratio of the gram of oil, drying oil, remember drying oil, that is employed, or that will be employed in the resin synthesis. I'm also going to explain that. And the next thing is to know the actual weight in grams of the resin itself, the total weight in gram of resin you're going to produce. You should also bear that in mind. Total weight of resin. So guys, this is what I would say about this particular one. It depends on how many gram resin you aim at synthesizing. For the purpose of this lecture, we'll be working on a 300 gram resin. We want to synthesize a 300 gram laboratory use resin for the formulation of a paint. So 300 gram is quite okay. So 300 gram for each of these oil lengths. So from here, we need to determine how much of the oil we're going to weigh for a 300 gram resin alkyd synthesis. Okay, now we can easily start by calculating that. And now I'll need you to understand that for a 40% alkyd resin oil length, all we need to do, since we want to synthesize a 300 gram resin, so 40% of the oil just means 40 divided by 100 times total alkyd weight, which is 300 gram. That would give us 120 gram, meaning that we'll be needing 120 gram of the oil, of the drying oil. Very important, very important. So we go to the 50% for a 50% alkyd resin. So we do the same calculation times 300. So this will give us about 150 gram. So we need 150 gram of the drying oil for a 50% formulation and for a 40%. Then likewise for a 60%, this for the long alkyd resin. So we'll have 60 over 100 times 300. Remember, 300 is variable depending on what total weight of resin you want to produce. So this will give us 180 gram. Okay. Now these are just the various weights in gram of the drying oil of the various oil lengths of alkyd resin we want to produce, and also get to make or manufacture a paint from. So this should be actually noted for our 300 gram formulation. Now, since we've been able to establish the various weights of drying oil that we will be measuring in the course of the synthesis, 120, 150, and 180 for the short, medium, and long alkyd resin lengths. So these are the 3 we'll be preparing. I would be explaining on how we're going to synthesize the 40%. So the same method will be employed for the synthesis of 50 and 60% alkyd resin length. And bear in mind that my drying oil has saponification value, very important. These are what we should bear in mind. Should range between 150 to 195. My drying oil sesame seed has saponification value of 172.13 milligram per potassium hydroxide. You see, is actually, this value actually lies in the region of the drying oil. The drying oils are what we are after, and should have saponification values between 150 to 195. Like I said, how to carry this out is attached in this video description. That's the saponification value, how to determine that. We wouldn't be going into that. So let's continue with the resin synthesis. So these are the four the parameters you have to actually get to determine first for your drying oil before you start carrying out the resin synthesis and calculations that follows it. So now we will be treating these other parameters here. So guys, the next thing we are going to do is to go into the synthesis proper, how to measure the required ingredients. Bear in mind, we are working with, for the first stage of the synthesis, of course, the reagents that we will be employing. We will be employing the oil, which is our drying oil. We would also need phthalic anhydride, and glycerol, which is our alcohol. So we have glycerol. Okay. So our phthalic anhydride is basically benzene 1,2-dicarboxylic acid. That's phthalic anhydride. Then glycerol is propan 1,2,3-triol. So we need a triol. So we have these reagents that we will be calculating to actually get to employ it in the synthesis of the Alkyd resin. So now we're going to make a table like this. We have saponification value of the oil. We already know it's 172.13 for the oil I'm employing. Okay, this is an example. So we get to have let's call this weight. Let me make the table. Sorry, let me call it our ingredients or our reagents. So we have the oil, which is our drying oil. Then we have the phthalic anhydride, which is benzene 1,2-dicarboxylic acid. Then we also have glycerol. Okay, now we're going to have a column for the weight of this for a 40%. Please bear in mind, we are synthesizing a 40% Alkyd resin length. So, and our drying oil DO has saponification value of this we've already determined. So now the weight of the drying oil, remember, we calculated the weight of the drying oil and find out it was 120 gram. That's 40 over 100 times 300 gram. Remember, we want to synthesize an Alkyd resin weight of 300 gram, and that gives us 120 gram of the oil. So here we'll be having drying oil weight to be 120 gram. Now the anhydride, benzene 1,2-dicarboxylic acid, we don't know the weight that we would be employing for a 40% Alkyd resin. We could call this X. We're going to determine that. And also for glycerol, we don't know it. Okay, so we go to another parameter, and that parameter is called the equivalent weight. So let's designate it with capital E, the equivalent weight. I'm going to explain what that is and show you the formula so that we could do it together and impute the values. So we also have what is called the equivalent mole. So let me designate it with equivalent mole E0. Okay, then we have what is called equivalent acid. So these are what we should determine. And we also have, finally, we have the functional group number. Let me call it F, functional group number. Then we also have the number of moles. We call that N. Let me call that N0. Okay, these are just what we need to actually get to find out for a 40% alkyd resin of weight of drying oil weight of 120 gram. So we are going to solve this out before we continue. So you can just take note of this. Then we go to the next stuff. So guys, you should have a table like this for your calculation. So we have the actual weight of our ingredients, okay? That's the drying oil, the phthalic anhydride, and glycerol. The combination of these three make up the resin. This is just what we're talking about. The resin itself has to, the alkyd resin, so to say, the alkyd resin. Drying oil, phthalic anhydride, and glycerol. These are the actual weights, but we don't know that of the phthalic anhydride and the glycerol. So X and Y, weight of 120 grams for the 40%. Okay, the same way we are carrying out the 40% is the same way we are going to carry out for the 50% and 60%. So this is called the equivalent weight, and this is called the equivalent mole, and this is the equivalent acid. This is the functional group, number of functional group present in the drying oil, number of functional group present in the acid anhydride, and that of the glycerol. And lastly, you have the number of moles. So once this is taken, let's go to the next stuff. That's to actually get to determine each of these now. Now let's first of all determine the functional group number, the number of functional group. Okay, we are working with a drying oil, and oils are esters. Oils are esters, definitely. Since they are esters, they have just one functional group. So the drying oil has one functional group being an ester. Then we also have the anhydride, that's the benzene 1,2-dicarboxylic acid. Let me draw the structure. Here. So this is our acid anhydride, benzene 1,2-dicarboxylic acid. So we also have propane 1,2,3-triol. So this is propane 1,2,3-triol. You can see these are their structures, and we just need to determine their functional group number. So for the benzene 1,2-dicarboxylic acid, as it implies, two functional groups are there for the anhydride. Okay, that's these two. So we have two functional group number for the phthalic anhydride, benzene 1,2-dicarboxylic acid. Then for glycerol, you can see we have 3. Use a triol, so we can put 3 over here. Now the next thing we are going to determine is the equivalent weight, which are actually designated with capital letter E. Let me write out the formula for the equivalent weight, so we get to calculate for the 40% alkyd resin oil length. So now to calculate for the equivalent weight, which is E. So the formula is given by molecular weight over functional group. That's the number of functional group. That's F. We call this Fn, the number of functional group. This is how we get to find the equivalent weight for drying oil, phthalic anhydride, and that of the glycerol. Okay. Now for the drying oil, which is 120 grams of weight, we can get the equivalent weight by molecular weight is different from this. This is just the actual weight in grams we will be measuring for the oil for the resin synthesis. So the molecular weight is has its own formula. So I have molecular weight of the oil, in particular for the oil. This is for the drying oil, and the formula is 56 0.11 times 10 raised to the power 3. This is a factor, okay, divided by what is it called? The saponification value, which we've determined earlier, SV, saponification value. And for this, we have 56.11 times 10 raised to the power 3 divided by saponification value, which is 172.13. Now, if you do that correctly, you'll be having value 325.97, if I'm not mistaken, gram. Okay, so this is the molecular weight of the drying oil, which is our equivalent weight. Okay, sorry, this is our equivalent weight. Okay, molecular weight is just this formula. So our equivalent weight is now going to be molecular weight, which is this value, divided by the functional group number, which is 1. So 325 divided by 1 is still 325. So here we still have 325.97. Okay, so let's go to the next one. For the benzene 1,2-dicarboxylic acid, let's determine its equivalent weight. Now for the phthalic anhydride, let me say PA. What's the molecular weight of phthalic anhydride? That is, let's draw the structure again so we could determine the molecular weight. H. So looking at it, we're going to sum the total atomic weight to find the actual molecular weight of this compound. So we have how many oxygens? We have 1, 2, and we have 3. We have 3 oxygen atoms, that is 3 times 16. The atomic mass for oxygen is 16. So 3 times 16 plus hydrogens, we have 1, 2, 3, and 4. 1, 2, 3. Yeah, so we have 4 times 1. So we have carbon. You know, each of these points are carbon atoms. So we have 1 here, 2, 3, 4, 5, 6, 7, and 8. So we have plus how many carbon atoms? That is 8 times 12. 12 grams for carbon atom. So we have this. So once you do this correctly, (148 grams). So this is our molecular weight for the phthalic anhydride. So to determine now the equivalent weight, we substitute ahead and says, then substitute molecular weight is 148 divided by functional group number for phthalic anhydride. This phthalic anhydride, remember, there are 2 functional groups, dicarboxylic acid. So we have 148 divided by 2. And once you do that, you have value 74 for the equivalent weight. Okay. So you also do the same. We also do the same thing for glycerol. Glycerol, let's write out the structure. So we have this as our prochromatography trial. Now looking at it again, how many hydrogen atoms can we see here? We have 3 hydrogen atoms. Oh, not just 3. 1, 2, 3. This is 1, 2, 3. There are 2 here. So we have 5. We have 7. We have 9. 2, 2, 2, 6, 7, 8, 9. So we have hydrogen atoms 9. Let's say hydrogen plus we have carbon, we have oxygen. Okay, so hydrogen we have 9 of it times 1. Okay, plus carbon we have 3, 1, 2, 3, which is 3 times 12 atomic mass of carbon, plus oxygen we have 3 also, which is 3 times 16. Okay, so we get to add that up. 9 times 1, so we have 92 of glycerol to be the molecular weight of glycerol. That's proton 1, 2, triol. Then we also use the same formula for the equivalent weight. Remember, equivalent weight. So we need to find that of glycerol. So that is molecular weight 92 divided by functional group number 3 alcoholic groups, OH groups. So we have divided by 3. Okay. So 92 divided by 3 should give us value 31. 31. So this is how you can find the equivalent weight for your ingredients. So now we go to the next one, equivalent mole. It's subscript 0 is given by the formula weight of sample divided by equivalent weight. So we need to know the weight of the sample. Weight of sample divided by equivalent weight, right? Equivalent weight, which we found out previously as that is our E, equivalent weight. So weight of sample divided by this value will give us our equivalent mole. Okay, there are reasons why we are finding this, because we're going to use these values that are very important in the getting to know the actual weight of this ingredient to measure and get to analyze. So weight of sample is equivalent mole is weight of sample divided by equivalent weight. Now for the drying oil, we want to find the equivalent mole, this one. So weight of sample 120 gram divided by equivalent weight, which is this. So I have 325. Okay, 25.97 gram, okay, which is 0.3681. So we're going to put it here, 0.3681. All right, then we're going to find that of the phthalate anhydride, the same formula, weight of sample. Now what is weight of sample here? We don't know our weight of sample. So for the anhydride, our reagent, the equivalent mole, weight of sample unknown, divided by the equivalent weight, which we got to be 74. You can still put it here, x over 74. Likewise for glycerol, this is y, weight of sample unknown, divided by equivalent weight, which is E, to be 31. So guys, we have this. Now the next thing we're going to find out is our equivalent acid. So we have the formula for equivalent acid to be weight of sample, same formula to that of the equivalent mole, weight of sample divided by the equivalent weight. Same formula for the equivalent acid. Now we get to look at it. Drying oil, oils are triglycerides. Triglycerides are esters. Esters are composed of a triol, an alcohol, and with a fatty acid. So definitely our drying oil contains some level of acid in it. So definitely we're going to apply same formula, weight of sample 120 divided by equivalent weight, which is 325.97. Definitely we are still transferring this to this other side, so we still have the same value, 0.3681. okay, now we do for the anhydride. The anhydride is an acidic one, so it's acidic. Definitely we can easily find out the equivalent acid, by doing the same thing. So equivalent acid is still the same thing as X equivalent mole, that is X over 74. But in the case of the glycerol are alcohols, so they have no acidic functional group. They don't have this. Okay. Instead, the glycerol contains this. So making it basic, it is not acidic. So in that respect, so we won't be having any value for the equivalent acid. Now, finally, we're going to find out the mole, number of moles designated with M subscript 0. So for the number of moles, MO, the formula is weight of sample, weight of sample divided by molecular weight. So what is the weight of the sample for the drying oil? For the drying oil, we have weight of sample to be 120 divided by molecular weight, which we'll find out using the other previous formula. So that's this value. This is the molecular weight, equivalent weight, which is the molecular weight. Okay, the equivalent weight is actually the molecular weight of whichever ingredient, that's this ingredient we have here. So we have weight of sample to be 120 grams divided by molecular weight, which is this equivalent weight here. So I have 325.97. So for this is for the oil, so I have 0.3681. Okay. So for our acid anhydride, phthalic anhydride, what's the weight of sample? We don't know the weight of the sample, so it's going to be X divided by the molecular weight. The molecular weight, which we found out earlier, we calculated that to be 148 grams. So we have 1 over X over 148. So that's what we have here, X over 148. Okay. Then lastly, that of the glycerol. The same formula for the number of moles. You have Y, which is, we don't know the weight of the sample yet, divided by Y over 92. So I have Y over 92. So this is how you prepare the table for the 40% alkyd resin. The same thing goes with that of the 50% and 60% respectively. So the only difference is your weight in gram and the calculations that come forth. So now from here we're going to be determining what is called the Alkyd constant. The formula for the Alkyd constant, which would be also determining. So the Alkyd constant is expressed as the summation of the number of moles divided by the summation of the equivalent acid. So the summation of this divided by the summation of this will give us the Alkyd constant. Okay, this is just for recording purposes. So now let's head into the main calculation to finding out the actual weight in gram of the drying oil, of the acid anhydride and the glycerol that we would be weighing into our 4-neck or 3-neck gram bottom flask for the synthesis of the alkyd resin. This is just the most important aspect of synthesizing the alkyd resin, getting to know the actual weight of this ingredient to weigh before starting up the synthesis proper. Now we're going to make we're going to have a relationship that could give us the actual weight of the acid anhydride and the glycerol in combination with the oil that we would be employing for the synthesis. So that relationship, we should have weight of oil plus the acid anhydride, that's phthalic anhydride, let's call that PA. That's the weight of the phthalic anhydride, and that of the glycerol, let's call that GL1, for a 300 gram resin formulation. So I'm equating it to that so that we get to find out what weight of the anhydride glycerol that we would be employing for a 40% alkyd resin length. So for the 40% alkyd resin length, this is a relationship that could help us to find out the actual weight of the acid and the glycerol that we're employing. So weight of oil, remember, for a 40% we have it to be 120. We don't know that of the acid anhydride. We designated it as X, and that of the glycerol as Y, equals to 300. So we have this equation which we can actually rearrange, so we can have X plus Y equal 300 minus 120. So we're gonna have, that's 180. So let's call this equation 1. This X stands for the weight of acid anhydride, benzene 1,2-dicarboxylic acid that we would need, we'll get to weigh for the synthesis, and this stands for that of the glycerol. Now, there's something we need to also put into place. We know that alkyd constant K is designated as summation number of moles divided by the summation of equivalent acids. We know this relationship, right? And we know what the number of moles are. From our previous table, we have it to be for the individual ingredients, for the oil, the phthalic anhydride, and that of the glycerol. Okay, divide by the equivalent acids of the oil, the phthalic anhydride, and that of the glycerol. Okay, so this is what the alkyd constant is all about, which we would also need to derive our second equation. Bear in mind, this is our first equation, so we need this expression, the alkyd constant, to derive the other equation. Okay, so we have, I'm going to wipe this off, of the oil from the table that we've actually derived is 0.3681 plus that of the anhydride. We got it to be X over 148 if you refer to that table, X over 148. Now plus that of the glycerol, also refer to that table, you would see we got Y over 92. Okay, divide by equivalent acid. You know, the oil is acidic, so we still have the same value, right? We derived that earlier on, plus that of the anhydride. We got it to be X over 74 from that table. You can refer to that. And that of the glycerol is not acidic, so we don't expect any equivalent acid value So we stop it at that. So we have this expression to work out. Now our Alkyd constant is a constant. Alkyd constant is 1.02. It's a constant. We wouldn't be going into the derivation of the Alkyd constant, but this is the expression, and that constant is 1.02. So the whole of this is equated to 1.022, equated to 1.02, which is the Alkyd constant. Very important. It's a constant. We don't need the derivation here. So we just have to know the value that the Alkyd constant for the resin synthesis or resin synthesis general is 1.02. So the whole of this expression equals 1.02. So let's break down this equation and get something like this, find a similar expression to equation 1. So let me rewrite this here and explain. So I've just written this, okay? So we're going to solve this expression to get our mass in gram of the acid anhydride and our Y, which is our mass in gram of the glycerol. So first of all, we could just cross multiply these values this way. The whole of this multiplies the denominator, the whole of this denominator multiplies the numerator over there. So we have this expression 1.02 multiplied by, I'm going to open a bracket, 0.3681 plus x over 74, which will be equal to 1 multiplied by the whole of this is the whole of that. So we have 0.3681 plus x over 148 plus y over 92. So we now have this expression. We can go ahead to open up the bracket. 1.02 multiplied by this one. So I'm using this one to multiply this, also using this one to multiply that. So this multiplied by that will give you 0.3755 plus this multiplied by that will give you 1.02 times x, that's 1.02x divided by 74, which will be equal to that expression. So we now have this expression. As you can see, we can actually rearrange this expression in the sense that we have this and this common terms. They have no letters attached to them. This and this are common. They have x. This is not common. Okay, it's the only variable that's left behind. So let's collect like terms for these two. So I'm just going to write this one. Then this value crosses over the equality sign. So we have 0.3755 minus 0.3681, okay, equal to whatever that is left, which is this value and this value. So let's start with this one. Bear in mind there's a common factor here, so I write this one first, x over 148. So this crosses over to the other side to change to minus. So I have minus 1.02 x over 74. Then we have just this one that's left, plus y over 92. So now we have this expression. If you could go ahead and subtract this value, we'll have 0.0074 for this expression. So we still have the same value, x over 148 minus 1.02 x over 74 plus y over 92. So now we are left with this expression. Of course, we would have to simplify this expression further. And how to do that? Let me rewrite it from the top and explain. You agree with me, this is something as over 1. So we're going to find a common multiple for these individual variables. So I'm going to have this thing. So remember, this is 0.0074 divided by 1. So what could be their common multiple? I've solved that already. You know, the common multiple between these two x variables is 184 when you get to find out the the lowest common multiple for these two. So it's 184, right? But then this is just the only variable left. To make it easier, what I did was find the common multiple of these two. You can do that, or you can just write it out, 148. Then you have 74. Okay, you could start with using 2 to divide through these two. So 37, here is 1, here is 1. So I multiply the whole of this. So that will give me 48 for these two x variables. So since it's 48, this is why. To make things easier for me, what I did, or what you should do, is multiply 148 for this lowest common multiple by this one. So I'm going to have 148 multiplied by 92. So I'm going to have 148 multiplied by 92, which will give us 13,616. Okay. Now this is going to serve as our lowest common multiple here, you know, to actually get to solve this expression. So 13,616 divided by 148, that will give us 92. So 92, this divided by that is 92. 92 multiplied by x is 92x. Put your minus sign. That will give us 184. Okay, right? Then 184 multiplied by 1.02, that will give us 187.68. Remember, there's an x here. Put your plus sign. Now 13,616 divided by 92 will give us 148. Of course, 148 multiplied by y is 148y. So we now have this expression. From here, henceforth, you can also choose to cross multiply. Yes, you can do that. Remember, there's an equal sign here, so we just get to cross multiply. So this multiply by that one. So we would be having 13,616 times 0.0074 equal to 92x minus 187.68x. That will give us minus 95.68x plus 148y. So we have something a little more simplified. So when you get to multiply this value by this value, you're going to end up having 100.7584, which will be equal to minus 95.68x plus 148y. So you can see the expression we now have. Then remember, our equation 1 says x plus y equals to 180 from the 300 minus 120, that is 180. So x plus y is 180 from equation 1. So we have to rewrite this equation in the sense that it's going to come in the order x plus y. Okay, now I'm going to transfer this value to this other side. I'm going to transfer the whole of x plus y to this other side and transfer this one over to the other side. So whatever sign these ones bear, they are going to change. So this transfer to the left hand side is going to be 95.68x plus 148y transfer to the other side is going to be minus 148y. Okay, I'm only transferring them such that it rhymes with equation 1, which is x plus y. So x plus y should come first, so x and y. So which is equal to, this value goes over to the other side. Bear in mind there is a plus sign here which is invisible, so it's going to be minus 100 here. The sign is going to change to minus 100 plus 7584. So from here now, guys, we can, this is now our equation 2. Equation 2. Now we can now write our equation 1, which we earlier got to be x plus y equals 180. So this was our equation 1. Now we're going to solve these two equations simultaneously to give us the masses of the anhydride, which is x, and that of the glycerol, which is y. So let me rewrite that and let's solve it. So basically what we're going to do here is to solve these two equations simultaneously by involving, let's use a simpler method for this solution, that is the elimination method. The elimination method just implies that you get to multiply this equation, the first equation, by the coefficient of x of the second equation, and multiply equation 2 by the coefficient of x in the first equation. You can see here. So the coefficient of x in this second equation is 1, is only 1x. So I'm going to multiply 1 to the equation at the top, numerator, then multiply this second equation by the coefficient of the first, which is 95.68. 95.68. That way I should be able to easily eliminate the variable x to find the variable y. So 1 multiplied by the whole of this expression will still give you the same expression. So I still have 95.68x so this multiplied by that, 95.68 multiplied by x, is going to give me 95.68x plus, there's a plus sign, 95.68x multiplied by y, 95.68y equals 95.68 multiplied by 180. That will give us 17,222.64, no, 0.4 rather, sorry. So we would have this expression. So let's go ahead. So we now subtract these two expressions. We're going to subtract them. Once we subtract them, this will go up from this equation. This will subtract out. Then we have minus minus, which is plus, and plus plus is still plus. So we're going to add these two expressions. That's 148y plus 95.68y, which will give us 243.68y equals, this is minus, minus minus is plus, so I'm going to add these two variables. If I get to add them, I'm going to have 17,323. Don't forget 1.1584 is what I'm going to have. So easily I can find the value for y. Remember, y is glycerol. So our weights of glycerol in gram to be measured would be dividing these two sides by the coefficients of y. So glycerol, which will be this 17,323.1584 divided by 243.68, and that will give me y. I will have 71.09 gram. So this is the actual weight in gram of glycerol that would be required for this synthesis. So since we found that, we can as well get to find out the mass in gram of the phthalic anhydride benzene 1,2-dicarboxylic acid, which I'm just going to refer to the first equation. Remember, first equation says x plus y equals 180. So let me just clean the top and find the other mass in gram of the acid anhydride. Remember, from equation 1 we had x plus y equals 180. So we now found our y to be 71.09. So I'm going to just substitute x plus 71.09, okay, equals 180. So I'm only substituting this. This is 71.09 from this, okay. So we now get to find x, collecting like that. X will be equal to 180 minus 71.09, okay. So we're gonna have our mass in gram of the phthalic anhydride, that's the benzene 1,2-dicarboxylic acid, that we would be needing for the measurement. So 180 minus 71.09 will be 108.91 gram. So guys, this is how you get to know the actual weight in grams of the ingredients for the Alkyd resin synthesis. So in summary, for a 40% oil length, remember, if you refer back to my other video, so for a 40% Alkyd resin oil length, you need your drying oil of weight 120 gram. Remember, we are working on a 300 gram Alkyd resin formulation synthesis. So drying oil 120 gram, and we need our benzene 1,2-dicarboxylic acid, that's phthalic anhydride. We just found out that we need exact amount to be 71.09 gram. No approximations in your measurements is very important. You use the actual weight. Then we also need our glycerol to be what we just found, 108.91 gram. So guys, this is just how you get to find out the actual measurements to take for each recipe in the resin synthesis. So just the same way I've solved for the various masses, weight in grams required for these reagents, same way you also find for the 50% Alkyd resin oil length, and likewise the 60% Alkyd resin oil length. So for the synthesis process, the Alkyd resin synthesis process, I'm just going to shed more light on the stages involved and how you can actually monitor the reaction progress. And the first stage is called the alcoholysis process. You could refer to my previous video to understand better of that process. So the alcoholysis process basically entails, but before that, let me list out the reagents that we would be needing for both stages of the alkyd resin synthesis. So we have, for the 40% alkyd resin length, we have our oil to be 120 gram, right? We have our phthalic anhydride is 108.91. We've calculated that before, and that is our X value, if you remember. So we got it to be 108.91 gram. And we need our glycerol, which we calculated to be 71.09 gram. So this is just for the 40% alkyd resin length. Bear in mind the same process involved in that we actually carried out to get these values are the same process, the same steps we are going to use to actually carry out the 50% alkyd resin length and the 60%. So these are the reagents we'll be needing. The oil, okay, we need this, we need that. So we also need we need to prepare a 0.1 molar potassium hydroxide. You can easily do that one. So we'll be needing this concentration because we'll be determining the acid value of the alkyd resin for the second stage. So we would need this solution available, and then we would also, an indicator which we would need is phenolphthalein indicator is needed. So, and the actual concentration you're going to be making is dissolving. You're going to dissolve 0.5 gram of phenolphthalein indicator into a ratio of 1:1 ratio of toluene and ethanol. So equal mixture of toluene and ethanol depending on how much you want to mix up. You dissolve 0.5 gram into 25 ml of equal mixture of toluene and ethanol. So you have this, okay? So 0.5 gram dissolved in equal mixture of toluene and ethanol will serve as your indicator. Then you also need, what is it? Let's see what is left. Xylene. And bear in mind your catalyst, yes. So we have xylene, and xylene should contain, the quantity you're going to be having here should contain 10% of the total alkyd resin, total weight of the alkyd resin. So 10% of the 300 gram formulation times 300 gram, if that is what you're going for, that is about 30 gram is that's 30 gram. So you would need this quantity of xylene. Xylene helps to remove the water of esterification during the course of the second stage of the synthesis. Then you also need your catalyst, and we are employing calcium oxide as catalyst, which should contain 0.1% of total alkyd resin weight, and 0.1%, that is 0.1 over 100 times total alkyd resin, which is 0.3 gram. So these are the reagents for the synthesis of alkyd resin. And we also need methanol. Lastly, methanol will be used in the second stage, in the first stage, for the solubility determination of the alkyd resin. So we will need methanol. So let me break down now the individual stages, and you get to know exactly when to use the reagents in various stages. We need to know our apparatus. So the apparatus needed, I've just listed the reagents that we would be employing. So the apparatus needed, we have a 4-necked round bottom flask, 4-necked round bottom flask for convenience, and we also need a mechanical stirrer, and we need a nitrogen gas. We need a nitrogen gas, the cylinder, to provide an inert atmosphere for the synthesis. So we also need a condenser. Condenser helps to, helps to cool the reaction because it's highly exothermic. So you have to connect a condenser. I'm going to illustrate it. I'm not in the lab to do this right now, and I can't actually go to the lab at the moment, and it's quite a different kind of, ball game in. So we also need a DIN on stock, apparatus. And what else do we need? Yeah, we need constant water supply, very important. And we also need power, electricity, to aid us with the mechanical stirrer. Okay, so now these are the apparatus that we need, the basic apparatus we need. So other things, your conical flask, your beakers, you should have them for your titration. Now for the setup, that's for the first stage of the synthesis. Okay, we need to have our 4-neck round bottom flask. I'm just going to be explaining this on the board. Sorry, I can't do that in the lab right now. It's very, very far from here. So I'm assuming this is our 4-necked round bottom flask. Okay, these are 4-necked round bottom flask. You can see the 4 sides of the round bottom flask. Okay, so now the one at the middle, this neck, one of the necks should serve for the mechanical stirrer. One mechanical stirrer should be inserted here. You have mechanical stirrer, which is connected to a power supply. Okay, so we have one other inlet should serve for the nitrogen gas. So you could have a gas cylinder of nitrogen gas, and the gas cylinder should be supported with a drying agent like silica to actually help to dry the gas coming from the nitrogen gas. Okay, now with a pipe connected into one of the inlets, okay, supply of nitrogen gas, well cupped, it should be well closed and well fitted. So we have a drying agent here. Silica to dry the gas to avoid impurities other than nitrogen to get into this round bottom flask. And this round bottom flask is fitted with a heating mantle. Now the temperature required for this heating mantle is from 200 to 250 degrees Celsius. So this is the operating temperature of the heating mantle. Then we also need to have this place, the other opening closed. From here we can withdraw aliquot or introduce reagents. Okay, we can use this to withdraw aliquot or introduce reagents. So for aliquot collection and testing even the temperature drop, you can use that. So then the 4th valve should be connected to a condenser. The condenser, we all know the condenser. The condenser has 2 outlets, one for water. So it's going to be connected here. One inlet of the condenser should be connected to a water supply. So let me open this place a little. So we all know a condenser has two inlets, okay? One inlet and one outlet. So this should be connected to a constant water supply. Water supply, okay? Then the outlet should be connected, should be wired or transferred to some system, okay? You are not using this one. So all you need is a constant water supply that would condense, and the condenser has a valve that goes in here. So once the water is constantly running and going off, it is helping to cool the reaction system. So this water has to be constantly running. Your nitrogen gas fitted, your mechanical stirrer, okay, fitted right in, which should be halfway through the round bottom flask. You shouldn't touch the base so as not to crack the round bottom flask. So the mechanical stirrer should be somewhere halfway. Okay, now this is just the setup. This is the setup for the first stage and the alkyd resin synthesis. So we have the four-neck round bottom flask, one valve for the Alkyd collection. You should close this because this reaction occurs in a closed system and in the presence of nitrogen gas, making it an inert system. There should be no outlets left open. So this is quite close also. Mechanical stirrer, your condenser, your nitrogen gas. Operating temperature of the heating mantle is 200 to 250, and that is just the setup for the alcoholysis process. So in the alcoholysis process, the only reagents you are introducing are your drying oil. You're also introducing the glycerol. Remember, we've calculated exact amounts to be measured, 120 gram, right? And the glycerol that we've calculated to be 71.09, actual weight 71.09. That means we have to make use of our weighing balance to get this actual weight, exact amount of this reagent. So the next reagent we are going to be adding for the first stage, which is the alcoholysis process, is calcium oxide, which is our catalyst, which serves as 0.3% of the total alkyd resin weight. Remember, 0.3 gram. So these are just the three reagents that will be added for the first stage. Okay, now this first stage is called the alcoholysis process, as I've said earlier. So you have to introduce this weighed amount into the four-necked bottom flask with the heating mantle temperature raised to 200. For the first stage, you maintain at 200 degrees Celsius. For the first stage, remember, I'm explaining the first stage of the alkyd resin synthesis by this illustration. So for this first stage, the temperature should be raised to 200 degrees Celsius. And for you to know that, you have to actually check the indicator of the heating mantle, of course, adjust it. So at 200 max, once these have been introduced into the round bottom flask, you switch on your mechanical stirrer. It gets to start turning. Your nitrogen gas, you make sure the valve is opened for the gas to start going into the system. Your heating mantle setup, your mechanical stirrer in motion, your constant water supply, trying to cool the system. So you're going to run this heating process for about 4 hours. That is, from experience, you can only get to have your monoglyceride being formed. The essence of this first stage is to convert the triglyceride of the oil, which is an ester, to a monoglyceride. And for you to know that this has been formed, you have to heat it about 200 for about 4 hours. And for you to know when it has been formed, this is what you're going to do. You're going to be carrying out a test. I'm going to wipe this off, the what we call the solubility test in methanol. You have to test for the solubility in methanol. How do you do that? This is what you do. You take aliquots, very small portion of the Alkyd resin that is still boiling, not actually up to 2 hours, 3 hours. You withdraw aliquot from the system and test it in same ratio to methanol. You could choose, let's say, 5 ml, just very small amount, let's say 2 ml ethanol and 2 ml of the Alkyd resin. You've withdrawn aliquot, okay, you're testing for the solubility in methanol. So the solubility in methanol tells you that the first stage is complete. So what you do when you mix these two, you determine its solubility. Just equal amount of ethanol into this beaker then withdraw the aliquot. Make sure to close back the system, that's the round bottom flask. Once they are mixed up, shake them a little and check if the resin is soluble. Solubility is determined by the presence of clarity. When the solution is clear enough, when it's very clear and there is no indications of oily materials or oily appearance present, that is to say that the Alkyd resin, so there shouldn't be an oily appearance, but there should be a clarity in the solution when mixed. Okay, so once you have that formation, that's to tell you that the first stage is complete. And bear in mind that the first stage should last maximum 4 hours. 4 hours is a very slow, tedious, and a violent process, but you need to keep monitoring the heat. If at some point it's getting too exothermic, you have to reduce the heating mantle or to reduce the mechanical stirrer and increase it later on again, until you have the solubility of the Alkyd resin in 1:1 ratio of ethanol to be clear enough. So once that is ascertained, minimum of 3 hours, it can't be less than, you can't get the monoglyceride being formed under 2 hours. It's impossible. So maximum of 4 hours, 3 to 4 hours should give you the solubility that you so deserve. So once this is gotten, you can now allow the round bottom flask, you can switch off the heating mantle and allow the temperature of the system. The system I'm talking about is the mixture of the oil and the glycerol and the catalyst that you heated to about 200 degrees Celsius, maintained at that temperature to cool down to about 100 degrees Celsius or 120. So once the system cools down to about less than 120 degrees Celsius, okay, then that is when you can now start up the second stage. All right, so now the second stage is called the trans-esterification stage. So it's just an esterification process. The only difference is that once the system has cooled to about 120-100 degrees Celsius, you can then get to start up the reaction again. But before you do that, you have to add a measured amount of phthalic anhydride. These are the reagents will be needed now. Remember, for the first stage, we only added the oil, glycerol, and the catalyst. But for the second stage, you add to the same mixture while still cool, a measured amount of phthalic anhydride. So that was 108.91 gram. So you measure this amount of the benzene 1,2-dicarboxylic acid into the round bottom flask, as I've illustrated before. So you just have to add it there. Then you also add xylene, which represents 10% of total Alkyd resin weight. Remember, we've calculated that also to be 30 grams. Okay, we're going to add this and this in the second stage of the Alkyd resin synthesis. So once that is done, you don't get to start up the reaction yet. So you're also going to fit in a din and stock. A din and stock should be fitted to the condenser to collect the water of esterification, because the essence of adding the xylene is to remove water of esterification from the reaction mixture. So you have to connect a din and stock to the condenser, such that as the water is coming out from the condenser, it gets to go into the din and stock. Let me show you with an illustration. Yeah, so I'm not getting the actual what is it called, the actual drawing. So you just have to connect it. This is the water inlet. Remember, this is connected to the round bottom flask. This is connected to the round bottom flask, which is the system. This is the outlet. So we should have a beaker. This is the din and stock apparatus, which helps to collect the water of esterification from the reaction mixture. This is the condenser already fitted to the reaction mixture. So for the second stage, you're only fitting a din and stock to the condenser, such that water that is being removed from this place, not from the outlet, okay, from the top of the condenser into the din and stock, gets collected into a beaker or a measuring cylinder, preferably a measuring cylinder, because you need to be noting the volume of water being removed in the course of the reaction. So now, once you've added the two reagents, phthalic anhydride and the xylene, you are then allowed to start up the reaction again. But then this time, you're going to increase the heating mantle temperature to 230, between 230 and 250 degrees Celsius. And this process is going to last for about 3 to 4 hours again for the reaction to be complete. And in this case, for you to know when the alkyd has been formed is determined by the drop in acid value. Remember, we are adding an acid to the glycerol in the first stage. So you need to determine the drop in the acid value of this in the reaction system. And how to do that is, once you've started up the reaction, just give it like a minute, then start determining the drop in acid value. And in my previous video, I illustrated that you should prepare a table having time and acid value. I gave a formula for that, determining acid value. So at interval of 0 minutes, once you've started the reaction, after a minute, start up to take your acid value determination. What it means is that you withdraw aliquots between 0.5 to 0.65 ml of the reaction system at 0 minutes and determine its acid value. And for you to do the determination in acid value, this is where you have to titrate the aliquots which you've taken. You take 2 aliquots ranging whose volume lies between 0.5 and 0.65. 2 aliquots. So the time we have, let's say our beaker A, our aliquot 1 and aliquot 2. So at the 0 minute, we need to withdraw aliquots. Let's say we took 0.4 and 0.5 ml of the aliquot. We should be in the range of 0.5 to 0.65. So we determine the acid value. Okay. Now to determine the acid value, we titrate each of these aliquots against 0.1 molar potassium hydroxide. Now our indicator, which I've also illustrated in that video, and the actual weight, and I've just showed you guys. You take 0.5 gram into a 1-to-1 ratio of toluene and ethanol. So you dissolve 0.5 gram into that ratio, then that will serve as your indicator here. Okay, now let me draw some table that could help you to understand how to go about that. So we have this. So remember, we are taking some volume of the sample A and B, which is 0.4 and 0.5. Then we also should have a portion for volume of water being removed. Definitely at 0 minutes you wouldn't have any water being removed. Okay, then at 30 minutes, looking at the measuring cylinder connected to the din and stock, you get to notice some drop of water into the measuring cylinder, which you can actually get to record at the 30th minute. Okay, at the 30th minute, the same thing, you are going to weigh between 0.5 to 0.65. Let's say this time you'll be able to weigh 0.3 or 0.6. Okay, 0.6. Then probably you might have gotten your volume of water removed. Maybe taking for example 6.5 centimeter cube or 6.5 mil, depending on the unit you want to work with. So, but then you have to determine the acid value, and for you to do your titration reading, you can do that. You put your potassium hydroxide in the burette and titrate it against the acid which you've just collected as aliquot from the system. So guys, you're going to have a table that looks like this for your respective aliquots for determining the acid value the drop in acid value. And the acid value drop should fall down to as low as 10 milligram per potassium hydroxide. Remember, you are running a titration of your aliquot against potassium hydroxide using phenolphthalein indicator. Just as I've explained before, the amounts to be weighed, dissolve it in toluene ethanol mixture, then titrate it, and weight of sample, assuming you weighed 0.4, 0.5, which should lie in the range. You collect the aliquots 0.4 to 0.5. Bear in mind, once you take aliquots from the system, as the process is in progress, try to close it immediately. So probably you had maybe final burette reading to be 13.00, let's say 14 point, let's say 50. Okay, you can, this is the final burette reading from my initial value of 0.00. So you can actually get to find the average titer. The average titer value, this divided by that, the addition of this divided by 2 will give you the average titer. Multiply by this factor, then divide by weight of the sample, which you could even take as average, or you could do them independently. It's preferable to do them independently, in the sense that you find the average, you find the acid value for the first aliquot, find the acid value for the second aliquot, because for each 30 minutes or 0 minutes interval, 30-minute interval, you take 2 portions. We are running 2 portions. Then finally you take an average to get the exact acid value at 0 minutes, at 30 minutes, at 60 minutes, till maybe 240 minutes, thereabouts, till the acid value drops to 10 milligram per potassium hydroxide. Then your volume of water probably could have been 6.5 centimeter cube or 6.5 mil, depending on the time you're working on. So at the letter end, you have to find the acid value here. Titer value is 13 times 5.61 divided by weight of the sample is 0.4. So weight of the sample is 0.4, titer is 13, 5.61 is a constant. So you get the acid value for the first portion of the withdrawn aliquot. The same thing you get for the second portion. Then the two values, you get to find the average. That will give you the average acid value, which you could find out that it could be around 148.6 milligram per potassium hydroxide. This is telling you that even at 0 minutes, you still have a long way to go. So at another 30-minute interval, withdraw aliquots, repeat the same process. It gets to drop little by little till it falls to about 10 milligram per potassium hydroxide. And once you get to this point, that would tell you that your Alkyd resin has been fully synthesized. So guys, this is how you go about the Alkyd resin synthesis and how to do the necessary weighing, which must be exact, and the calculations.